Hello everyone and welcome to this video. Today I'm going to be showing my assignment 1 for Comp 3132, that is applied machine learning. Today we're going to be using the fashion MNIST dataset, exploring data and build a neural network, training it, and also analyze the performance, covering 21 key steps in this process. With the fashion MNIST already imported from Keras, we can start here in question 1. Here I use the shape method to see the dimensions of the images and the labels for train and test. Question 2, both the train labels and the test labels have lengths corresponding to their image counts, so 60,000 and 10,000 respectively. For question 3, here's some sample labels, and the first 5 training labels are 90030, and the first 5 test labels are 92116. Moving to the question 4, here we can examine the digital content of the image at index 5 in the training dataset. As you can see, it's represented by a 28 by 28 array of pixel values ranging from 0 to 255. For question 5, plotting this image, it reveals an item from clothing. And now for question 6, the label for this image is 0, based on the class list right here, representing a t-shirt and top. We can conclude that this image represents a t-shirt. So this step here in question 6 really helps us to visually connect the numerical data with the categorical meaning. Similarly, for question 7, we can inspect the digital content of the image index 500 in the testing dataset, which is again a 28 by 28 grid of pixel values. So you can see right here. In the question 8, it involves plotting this image, which clearly display another clothing item. And here for question 9, we can see that the label for this test image is also 0, like the previous example. This means that it's another t-shirt, right, from our data set. And this can actually confirm that our labels are consistent across both training and testing sets. Here in question 7, let's start to build our neural network so we can import models and layers from Keras. In question 11, it defines a sequential model called my network. And in the question 12, we flatten the 28 by 28 images into a single 784 neuron column as the input layer. Now the question 13 normalizes our pixel values by dividing them by 255, scaling between 0 and 1. This actually helps with training stability. For question 14, we add our first hidden layer with 512 neurons using the ReLU activation function. And on question 15, it adds a second hidden layer with 128 neurons, also using the ReLU. When you reach the question 16, our final layer is a 10 neural dense layer, and it's using the softmax as the activation function. We use the softmax here because it's ideal for multi-class classification problems like the fashion MNIST. It takes the raw output scores, it works like this, from the previous layer, and it converts them into a probability distribution. It means that each one of these 10 neurons will output a probability, indicating the likelihood that the input image belongs to that specific class. And all of those probabilities will sum up to 1. This allows us to classify the input image into one of our 10 fashion categories. Here in question 17, we compare two compilation options, the option A and the option B, as you can see right here. Where you can see here in the option B that it utilizes the RMS prop optimizer and the categorical cross entropy loss, so requiring one hot encoded labels. And after 5 epochs, the option A generally showed slightly better performance with a test loss of around just 0.37 and accuracy of 0.88, while the option B actually had a test loss of about 0.43 and an accuracy of 0.86. So the key difference is the loss function. So when it's dictating the label format and the optimizer, it also influences the training process and the convergence. In question 18, we extended the training for both option A and option B models to 10 epochs. It's, as you can see right here, both of them. Here we can also observe a general pattern. As the epochs increase, the training loss tends to decrease and the training accuracy tends to increase. However, you can see that the validation loss increases slightly after a certain point here, while the validation accuracy might also stabilize or show just minor fluctuations. So what we can take out of it is that the models continue to learn from the training data, but their ability to generalize to unseen data might not improve linearly with more epochs, hitting potential overfitting. So here the difference in the question 19 about the fashion MNIST and the MNIST is because the MNIST features handwriting digits, like from 0 to 9. That's relatively simpler and visually distinct, while the fashion MNIST, on the other hand, just contain images of clothing items like shirts, trousers, and shoes. this data set is considered more challenging because clothing categories can often be visually similar. So here in the question 20, the accuracy differences, we can see that different optimizers use distinct algorithms to adjust the model's weight during training. This actually affects how quickly and how effectively the model converges and find an optimal solution. And that's why we have variations of accuracy even with the same network. So here in question 21, we use the evaluate functions to assess our 10 epoch models for overfitting. So here in the model, for the model A, for the option A, we can see training accuracy around 0.91 and test accuracy around 88. So both models show a noticeable gap where the training accuracy is significantly higher than the test accuracy, and the training loss is always lower than the test loss. So this question just concludes the evaluation of this neural network that we just built here for the fashion MNIST dataset, and we also could identify a overfitting in this dataset. So that was the assignment, and thank you for watching the video.